Hello, everyone, and welcome to today's broadcast, Through the Looking Glass and What Amino Acids Found There, presented by Kirsty Penkman, Reader in Analytical Chemistry, Chair of Chemistry, Graduate School, Department of Chemistry, University of York. I'm Alexis Cross of LabRoots, and I will be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. Our speaker will respond to your questions via email. If you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Dr. Penkman. I will now turn the presentation over to her.
Thank you very much. So I wanted to give you a bit of an insight into the wonderful kind of world of analytical chemistry meshing with archaeological and earth science that's been my experience over the last few years. So please, I invite you to come through the looking glass with me to find out what amino acids found there. So amino acids are the basic building blocks of proteins. And of course, they're chemically very interesting because in life, amino acids exist in two non-superimposable forms, mirror images of each other, just like left and right hands, because of that chiral center that they all have, apart from glycine. Now, almost all organisms synthesize amino acids in the left-handed form, but actually this artificial dominance of the one form is thermodynamically unstable. And so once an organism dies or there's no more tissue turnover, this spontaneous reaction called racemization occurs until you get an equal amount of left-handed and right-handed amino acids. So you can think of it as the left-handed amino acid being the living amino acid and the right-handed, the dextro amino acid being the dead amino acid. Obviously, that's not what they stand for, but it's a good reminder of what you would expect to see once an organism dies. So at time 0, we would measure what we call a DL value. So that's just the number of D amino acids over the number of L amino acids. And that would give you a value of 0 because all your amino acids would be in the left-handed form. But when the organism dies, then a number of D amino acids gradually increases until you get to that equilibrium point where you have an equal amount of left-handed and right-handed amino acids over time. So you can use these proportions of left-handed and right-handed amino acids for a range of different studies. Now, I'm particularly interested in the kinetics of protein breakdown. It's also very important looking at the biological production of D amino acids, particularly from bacterial amino acids. And this has led me into two particular pathways, trying to understand chronology or timing and trying to understand past environments. Now, analysing fossil and subfossil samples is really interesting to me as an analytical chemist because these samples are they're very dirty, full of contamination. The analyte of interest is present in incredibly low concentrations. There's all this other stuff that you have to worry about. So analytically, they're incredibly challenging. But I think it's really important to remember that we shouldn't just be analysing fossils with our fancy machines just because we want to. It's very important to make sure that we are providing data to those people who have charge of those samples that is useful for their research questions, that's useful in questions of archaeology or earth science. And I kind of I show this through this very old Far Side cartoon by Gary Larson. These cavemen have gone to all the trouble of building this fancy microscope and they stick their mammoth underneath it and actually all they can say is it's a mammoth. Well, they knew that. They didn't need to use this fancy method of analysis to work out it's a mammoth. And so in my studies, what I'm trying to do is is really push the analytical methods forward by analysing these complex samples, but do it in a way that answers relevant questions to the collaborators. So I've got 3 case studies, which I'm hoping this shows that I want to talk about in this talk. So the first is looking at the dating work that we've been doing, marking time at a snail's pace. The next is extending that dating work, but going into realms that we never envisaged by building a better egg timer. And the last is to look at degradation in general through the Fading Star project. So marking time at a snail's pace. Now, the time period that we're in at the moment is called the Quaternary Time period, and it's characterized by these big swings in climate from very warm stages that we have today, so-called interglacials, to very cold stages. And the impact this has on the globe and particular regions of the globe is immense. So the top image you can see in the top right-hand corner is an artist's impression of Trafalgar Square in London 125,000 years ago, when we have a warm stage, and we have underneath those buildings are the incredibly rich fossiliferous remains of things like elephants, rhinoceroses, even hippos wallowing alongside the banks of the Thames. Now, in contrast, when we have these cold stages, these glacial periods, we get ice sheets as far south as London. So clearly massive climate change that is experienced by the flora and the fauna at that time period. Now, to put our current climate in perspective, it's essential that we look back at our past records to understand what's happened. But the big problem that we have is that we have these very detailed temperature records, as the graph that you can see on your screens, from the ice cores and from the marine cores. But on land, we only have these snapshots of information, and it's very difficult to date those because they're not part of a long continuous sequence. Now, many of you will have heard of radiocarbon dating. Radiocarbon dating is a fantastic method, but it only goes back to around 60,000 years. That doesn't even go halfway to the last time it was this warm in Britain. And so in order to make those links from the pockets that we have on land to the big global climate, we have to have a dating method. Now, amino acid stratigraphy was something that was developed in the 1960s and the 1970s, and they recognized that as an inherent part of any biomineral contains protein. If you look in the top right-hand corner, you can see this is an acid-etched image where the inorganic calcium carbonate is being etched away, and you just get these kind of long sheath-like proteins that actually form almost the scaffolding of the biomineral itself. Some people thought, well, actually, this is really interesting. Maybe what we could do is we could measure the amount of L and D amino acids from different materials, particularly shells. And those that have a greater amount of D amino acids will be the oldest, and those that have a smaller amount of D amino acids will be the youngest. And we can date using this method. And this seemed to work very well for a few years, but then some quite strange results started to feed in. And so by the time the 90s came around, this is the kind of thing that was being said about it. So Milford Wolpoff, who was a leading paleoanthropologist, who was cited in a science paper basically saying amino acid dating is some kind of joke. When my PhD supervisor was chatting about getting into amino acid dating, the person who's in charge of scientific dating in the UK, the English Heritage team leader, said, well, what on earth do you want to work on that for? It's the last refuge of the desperate. So coming into this as a PhD student, these weren't the most encouraging things I can imagine to hear. But I came into it thinking, well, can it work if we use the right material and if we really understand the chemistry underlying the racemization reactions? So in the intervening years, there's been huge advances. One of the key things is the analytical technology. So in the old days, you were able to analyze just one chiral amino acid pair, alloisoleucine and isoleucine, because it was very easy to chemically separate using ion exchange chromatography. But now we can separate multiple amino acids using reverse phase LC, and we've just updated this method as a UHPLC method, so being able to analyze very small samples. What's great about this is that these amino acids racemize at different rates, so it means we get different information from each of those. But it also flags up any contamination if we're starting to see unexpected changes in the extent of racemization against each other. The second advance has been in always analysing the free amino acid fraction and the total amino acid fraction. So proteins obviously exist as long chains of amino acids, but whether an amino acid is free or whether it's terminal or whether it's internally bound will affect the way that it racemizes. And so what we do is we take two independent subsamples from each sample. We break up one to give us just the free amino acids, and then the second we hydrolyze, so we break up all of those peptide bonds and we analyze to give us a measure of the total amino acid fraction. And that gives us two effectively independent measures of age on the same sample. It should be highly correlated. The third thing, which has been absolutely essential to the use of this method, is isolating an intracrystalline fraction of protein. Now, in most biominerals, like bone, the protein, although it's an integral part of the biomineral, it sits between the crystallites. Now, the problem with that is that if that means that the amino acids can leak out into the environment, they can, contamination can get into the system. They can also be affected by rate-affecting factors in the environment, such as pH, availability of water, metal catalysts, and so on. And so if we analyze just these proteins, then there's very little chance of it telling you something about the age of that actual sample. Now, some really nice work done in the 1980s showed that actually in some biominerals, there's a very small fraction of protein that seems to be physically entrapped within the crystal, so-called intra-crystalline proteins. Now, if we analyze just these, then there's a good chance of it telling us about the age of the sample. So what we do is we basically remove all of the protein that isn't trapped within the crystal. We only analyze the material in the crystal to basically isolate a closed system of protein that's breaking down predictably. So bibbidi-bobbidi-doo, put it together, and what do we get? We get what we're calling ICPD, or intracrystalline protein decomposition. So we've got a range of ways in which we can show the data, and one of the most useful mechanisms we use to check what the quality of the data is by looking at those two fractions that we pull from the same sample. So along the x-axis here, you've got the extent of racemization in the free fraction, and along the y-axis, you've got the extent of racemization in the total fraction. And what we would expect to see is that young samples fall towards the origin, so low levels of DL, and older samples fall towards the top right of the graph. And we would expect samples to fall somewhere along that line. Now, if you use the old method of dating, so looking at the matrix proteins as well as those that are intercrystalline, what you see is that a lot of samples do fall along that line, but an awful lot fall off to the right-hand side. Now, these are evidence that the material that we're analysing is not closed system. However, if we use the bleaching method, then we clean up this data beautifully. So by isolating just the bleached fraction, the intracrystalline fraction, we get this really nice coherence between the free and the total measurement. So we can be more confident in that the protein that we're measuring is degrading predictably in a closed system. Now, as the work continued, we started to realize that actually we need to concentrate not just on the organic fraction of the shell, but also on the inorganic fraction. So most shells exist in the form of calcium carbonate, and calcium carbonate can exist in two forms itself, aragonite and calcite. Also exists as basalt. That's less biologically important. Now, aragonite is actually unstable over geological timescales, and it can undergo mineral diagenesis to form the more stable calcite. Now, in the European record, we have some very interesting little snails called Bithynia. This is the Bithynia shell on your left-hand side, and its little opercula. An opercula is just the trapdoor the snail uses to shut itself away inside its shell. Now, the Bithynia shell is made out of aragonite, but its operculum is made out of calcite. So it gave us a really useful mechanism to test the difference in the mineral stabilities and what impact that had on the racemization. So here the graph you can see in your left-hand corner is the same as we've been looking before, the free racemization of, in this case, alanine, the total racemization of alanine against total racemization of alanine. And what you can see is these are all samples from one particular site, so we'd expect them to be all falling around the same age, around the same point. But what we can see is one clear outlier, sample 13. When we analyze the XRD of one of the samples that's sitting in the middle, you can see that we've got clear peaks related to the aragonite, but no indication of calcite in that shell sample, which is expected. But when we analyze FL13 when we analyse sample 13, we can see in that blue circle that we've started to get some mineral diagenesis of aragonite to calcite. Now, obviously, that's going to compromise our closed system of protein, even if it's for a short period of time, because at some point in time, that crystal has changed from aragonite to calcite. So if what we could do is analyse something that's originally calcite, that's unlikely to undergo that mineral diagenesis, then that will put us in a good position. Hence, we turned our attention to these much smaller opercula. So these are about the size of a sesame seed, but luckily they're very prevalent in most deposits. And so we started to look at these over a wide time scale. So here on the y-axis, you've got racemization, extent of DL, and on the x-axis, you've got 1,000 years BP. So this extends from time now all the way back to 3 million years ago. And what you can see here, I've just selected 3 of the amino acids that are particularly helpful over this time range. You can see that the aspartic is racemizing really, really fast, reaches equilibrium more quickly, but it gives us really great resolution over those short time scales. Something like valine in the blue is racemizing much more slowly, so that's not so useful over the short time scales, but it tells us about those longer time scales, getting us back to at least 3 million years. So we've been dating a whole range of different sites, initially in the UK and now across Europe. We've now dated over 150 sites, and this has given us critical data on the timing of climate pulses back to 3 million years. We've also been able to shed a lot of light on some archaeological questions. If you kind of go from the right-hand side of your graph downwards, that you're going from the earliest times all the way to the present day. And we've been able to kind of track the archaeological technology development with our racemization. So here in the oldest technology that present in Europe is the so-called Mode 1 technology, and we can see that coming in, and then development of these 2 technologies, the Clactonian and the Acheulean. And then at a certain point, about 300,000 years ago, we see this complete flip to a different technology called the Levallois technology. Now, I'm not an archaeologist, but I understand that the Levallois technology is a technological advance because for the same sort of volume of flint, it gives you a greater cutting area. And we see this real dominance of this Levallois technology after this point in time. We also see a lack of humans getting into Britain in that last interglacial, which fits very well with some of the ideas about the channel formation. And then we can track kind of humans all the way to the present day. And so a couple of years ago, an amazing exhibition which our work was a part of. Felt really privileged to be involved in this, was put on at the Natural History Museum and in London. And when I went down there to be able to see our work kind of emblazoned on the front of the building, that was a real career highlight, definitely. So, of course, now that we think we've got closed system protein in one type of biomineral, where we could look at a whole range of different types of biominerals. And as Alice in Wonderland would say, somehow it seems to fill my head with ideas. We've been looking at marine shells. We've been now starting to work on enamel material, which is very interesting. We've been doing a lot of work on corals, which has led us actually to look far more into the biomineralisation process to track things like coral bleaching events. And, you know, we're even working with tiny microfossils such as foraminifera. And I just wanted to highlight a couple of the studies that are most relevant from an analytical point of view. So the work that we were doing on the dating led us through to thinking about what other material we could analyse. And one calcitic material is eggshell. Now, we were particularly interested in ostrich egg shell, and that's because it's present in huge proportions in some very early human sites, particularly in the African and Arabian material. You get these incredible sequences of ostrich egg shell in cave deposits, and we've been very lucky to work with various researchers working on the Pinnacle Point cave deposits down in South Africa. And some of the very earliest evidence of art is found on eggshell. It's thought that it was used as a water container, so it was a kind of breakthrough technology in terms of enabling modern humans to travel. So it's a very interesting archaeological artifact. But of course, within the ostrich eggshell are the proteins that we could potentially use to date it. What made ostrich eggshell even more exciting was that the protein sequence was known, so the ordering of the amino acids along that protein chain. And so that means that we can study the protein breakdown not just using LC, as we had been before, but also using mass spec. And as an aside, you can get isotope data on the eggshell to tell you about paleoclimate. So it looked like a perfect material to work with. Now, when I said whether an amino acid racemizes or not depends on where it is in the chain, there's a huge network of reactions that have to happen in order to result in a racemized amino acid. Whether an amino acid is N-terminal, if it's C-terminal, that makes a big difference. If it's internally bound, some amino acids can't racemize at all, others can. If it's free, it tends to go relatively slowly, but by being free, it's probably gone through peptide bond hydrolysis, which means it has to be N-terminal. All of these affect the rates of the reactions. And so we wanted to study this in more detail. So we started to look at ostrich eggshell because of this known protein sequence dominated by struthiocalcin types 1 and 2. And these are C-type lectins which promote biomineralisation. So this is the sequence on the right-hand side. So it's a quite short peptide sequence. And we were particularly interested to start off with in trying to work out how valine racemizes. Valine is a relatively simple amino acid. We thought it would probably be quite simple to understand. And so what we did was we basically looked at the whole protein, but we also looked at these short peptide fragments highlighted here in red and in orange. So what we call EDVIG and WNSVWAW. So we wanted to look at the whole protein, but also these peptides. And so we undertook a whole series of artificial diagenesis experiments in a closed system environment within the eggshell. We then demineralized the material and looked at what would happen if it didn't have the mineral to protect it. We then looked at these very short peptides to see what would happen in those circumstances. And then we tracked these reactions using soft ionization protein mass spec and MSMS, variety of different methods, mold it off, electrospray, FT, ICR, to basically look at those mass shifts as the peptide broke down, and obviously a lot of that involved de novo sequencing of the products. And we were also tracking the extent of peptide bond hydrolysis and racemization using reverse phase LC. And so this meant for the first time we were able to track that protein diagenesis in real time to try and understand the mechanisms and the kinetics of the reaction. So this is just one of the examples. This is our little synthetic peptide, EDVIG. And so this is the top spectra is unheated, and you can see the molecular ion here. And then as we heat it for a couple of hours, 140 degrees C, we start to see that peptide bond between the D, the aspartic acid, and the V, the valine breakdown, and then we start to see generation of that VWIG fragment with the valine being N-terminal. Now, when we look at the extent of racemization, this fits really well. So this is the heating hours against the extent of racemization. And we start to see a very slow increase in racemization, probably because it's that peptide bond hydrolysis that is the sort of rate determining step. And then at that point, it can racemize. And then we start to see this increase as time goes on. Now, I like this egg timer project because it exemplifies how you should analyze everything. Because we ordered these synthetic peptides in, looked like a clean mass spec peak that they'd sent us, LCMS peak, and then we analysed it by LC. And what we found was that half of the peptide that has been sent to us wasn't EDVIG at all, it was EAVWIG. So in half of the positions, alanine had been substituted for the aspartic acid. Trouble is, we set up all the experiments, they were sitting in the ovens, half of them had been done already. So I just said, well, let's just analyze them anyway. Let's see what we see. And what I really love about this is it gave us some fantastic data. So actually, this was a perfect experiment. In half the places, you had substitution of alanine, and you can see how that alanine-valine peptide bond is inherently more stable, and therefore that valine doesn't become terminal and therefore doesn't racemize as quickly. So it's a beautiful experiment that we're writing up at the moment. So yeah, so if things go wrong with your experiments, don't worry, just analyze it, and they could give you some real diamonds of data. We also started to see in-chain racemization of serine. This was something that had been hinted at in our previous work. By degrading this particular peptide, WNSVWAW, we were able to show that the extent of racemization followed the patterns of aspartic, which racemizes in chain, rather than alanine and valine, which can't racemize in chain, therefore showing that actually the serine was racemizing within chain. Now, this is biologically very important. High levels of serine DL have been implicated in particularly degenerative diseases like Alzheimer's and Parkinson's and renal disease. And so one of the things we're doing is expanding this work to try and understand whether the racemization is a product of what we're seeing, or potentially if it's a cause. And either way, can we use this as a mechanism to track the mechanisms and the progress of disease? We then started to look at the archaeological material, and we started to go further and further back in time. As you look in the left-hand graph, this is the sequence of struthiocalcium-1 basically the proportions of the spectra that contained those particular amino, those particular parts of the sequence. And what you can see as time goes on, as you go down the plot, you get struthiocalcium preserved for a good length of time. By 150,000 years, you can still get the whole sequence out in your mass spec. But what absolutely amazed us was how there were particular portions of the peptide that were still sticking around by 1 million years and even by 3.8 million years from the middle of Africa. This is a site called Letoli, Tanzania. We were working with some very talented molecular modelers in Sheffield and at Warwick, and they did some calculations to look at the binding energy to the calcite surface of these parts of the peptides, and the domain with the strongest calculated binding energy to the calcite surface was the one that was selectively preserved in our experiments over million-year timescales. So it's a really nice synergy. So we are very confident these are original proteins. A little bit of work that helped us with that confidence was the work that we did using GC QTOF to look at some real volatile organic compounds. When we were preparing the eggshell, we quite often had could smell particularly burnt samples, but when we were crushing them or when we were demineralizing them, quite often got quite a strong smell from them. So there's obviously some sort of volatile organics within there. So we have a great atmospheric chemistry group here at the Department of Chemistry, and so I chatted to them about, well, what's the potential for us to actually analyze this material? Some really talented guys in our workshop, Chris Mortimer, basically prepared this inline sampler where we could crush the material and then inject it directly into the GC. And then it's not very clear in this image, but there's an olfactory port here in the middle of the image, and you basically pop your nose in it, eject the sample, and then you breathe, and occasionally it spits hot water at you, which is rather alarming, but you basically breathe in, and if you smell something, you write down the retention times and you write down the smell, and then it goes through into QTOF mass spec for identification. I have to be honest, when I started describing this, I was not very descriptive. Dusty, musty, fusty, turn up quite a lot in the books. And then I started to get a bit more into it. I've got burnt, damp summer day, mushrooms, cucumber, fruit gums. I've probably been sniffing quite a few of these VOCs by the time I got to those just more descriptive terminology. But what we were, in a way, staggered to find was still the presence within this eggshell of really very volatile compounds, particularly dominated by these thiols. Now, they can't exist unless it's a closed system. We must have closed system protein in there, which gives us real confidence that our peptides are being preserved, and that's why we're getting such great reproducibility and a breakdown of reactions. So up to this point, up to 2009, all of this intra-crystalline work was very theoretical. It was based on being able to chemically bleach the material and continue to bleach it and never be able to remove all the protein. But some really nice advances in the imaging technology, particularly by the Grease et al. group were able to show that these actually exist in abalone shells, and they did some really nice work showing that these kind of faceted voids exist within organic crystals, and that these faceted voids have extra carbon in it. And when you look at the size of them, they would, our proteins would fit really nicely in them. So I think this is probably the source of our intercrystalline material. So this took us into thinking a bit more about the biomineralisation processes. And so we were working in collaboration with Leeds and with Warwick and with Sheffield and Cornell, trying to sort of grow crystals incorporating amino acids. The Leeds group were growing the crystals, then we were analysing them for how many amino acids were incorporated in them, and then people were looking to see whether they were incorporated as single molecules or as kind of clumps. And then doing hardness studies. And you can see the change in morphology as you increase the amino acid concentration as you go down the page in the images of the crystals formed. But what was really interesting is that as you incorporate more amino acid into your crystal, so if you look at the top right-hand graph, the concentration of amino acid incorporated is on the x-axis, and the hardness of that material is on the y-axis. And you can see a really strong increase in the hardness as you incorporate more amino acids up to a certain point. What's really interesting is that this takes it from the kind of level of strength that you would need to break an ionic bond all the way up to the forces required to break covalent bonds. So it looks like that enhanced hardness, which of course nature has been using for millions of years, the enhanced hardness of that composite material is determined by the force that's required to cut the covalent bonds in the incorporated amino acids. Hence why biominerals are intrinsically more stable than their pure inorganic counterparts. So this has taken us into some really interesting worlds that I hadn't anticipated. So this egg timer project, we were able to recover peptides from archaeological eggshell for back to 3.8 million years. And why that's important outside of this study is that because peptides contain evolutionary information, because they change over time, that means we can track evolutionary changes in this type of material over those lengths of time. We were able to show the direct evidence of sequence effect on maximization and in-chain maximization of serine, and we came up with this really nice way of dating our samples, which is exactly what we'd intended the grant for in the beginning. So these really exciting serendipitous results, are really very rewarding. Okay, so Alice at some point through the looking glass says they'd had quite enough of the subject of age, she thought. So I wanted to give you a little bit of an insight into some of the other work that we've been doing, particularly the Fading Star Shining Light project that Kirsty High, who's a current NERC fellow, has been working on. So Starcar is a phenomenal site, very local actually, it's in Yorkshire. It's from around 11,000 years BC, and it's been called the Stonehenge of the Mesolithic. It's a world famous site because the preservation at the site was phenomenal, particularly of the organics. So you get these amazing harpoon points, decorative beads, you get some of the earliest evidence of carpentry in Europe, these worked wooden platforms. And what's really striking about this site is the huge number of red deer antler headdresses that appear at this site. So this is where the skull of a red deer has been cut with sort of holes either side, almost maybe to put kind of a thong through. And so it looks as though these have been used as headdresses, maybe for ambush hunting, maybe for some kind of wild parties. And it's, as I said, it's a world famous site, and it's even been immortalised by Playmobil. So these are pretty impressive headdresses. Now the site was discovered in the 1950s, and as I said, one of the key features about it was this fantastic preservation of organic materials, which obviously don't normally survive for that length of time. In the 1980s, there was some evidence to suggest that some of these organics had deteriorated a bit, but it was really in the 2007 excavations that people became more and more aware how in danger some of these artifacts were. There were very few finds. The antler that was found was completely flattened. The bone that was found was demineralized. If you have a look just at the bottom right-hand corner of your picture, there's a little animation here, which is basically the, oh, no, that didn't work. There was an animation there, which is showing how flexible, that's a piece of bone, but how flexible it was. You could actually move it up and down. You shouldn't be able to do that with bone. Now, there was very low pH measured at this particular site, and there was evidence that a lowered water table was due to basically a change in the drainage patterns of this agricultural site, had led to the water table kind of moving through the archaeological deposits on a seasonal basis, which was causing particular issues. So the problem was there was clearly an issue with the organic materials, but there was no data on what kind of time frame this could have happened in, how much longer the organics remains could have survived at Starcar, whether anything could be done to slow or stop the decay. And this was a real problem, and there was a very big meeting with various interested parties where actually we couldn't really answer these questions. So I put together a project with York Archaeological Trust, funded by NERC, to basically say we need the hard data to be able to answer these scientific questions properly. And so Kirsty was recruited as a PhD student, and she set up a whole series of different types of experiments, lab-based experiments, burial experiments, comparison with archaeological materials. Now, one of the critical things we had to work with in this project was trying to work out what methods of analysis we can use. So we wanted to be able to detect very low levels of deterioration. We needed the methods to be minimally destructive, and for wider take-up in the archaeological community, we wanted them to be kind of fast, cheap, and relatively widely available. And so we used a combination of different imaging, electron microscopy, SEM-TEM, chromatography, so reverse phase LC, PI-GC, XRD, spectroscopy like FTIR, elemental analysis, a range of different techniques to really try and understand the degradation of bone material and wood material. So by using these complementary techniques, we could get a really good insight into the breakdown pathways of both the inorganics and the organics. What we were staggered to see is that, for example, in the lab-based burial experiments, even after 1 year, the material in the Starcar soil was enormously swollen. You can see how degraded it was just within 1 year. You got mineral replacement from hydroxyapatite to gypsum just in that 1 year, which we could tell through the XRD. And when we buried the jelly bone, as we called it, those floppy bits of bone in the microbially active soil, we saw complete loss within just 1 year of this. So real, incredibly rapid degradation. So we wrote this up for PNAS, and I've just taken a quote from that paper. From a chemistry perspective, the tragic deterioration of the Starcar site has provided a unique opportunity to understand diagenetic processes that normally are absolutely invisible over research project timescales. But so it was really great for us to be able to see these kind of rapid degradation, but clearly from a cultural heritage perspective, that deterioration is irreplaceable, is an irreplaceable loss of unique archaeological environmental evidence. What was really important to understand is that actually there wasn't one solution for how to save the site. There are different mitigation strategies required for the different materials. If you wanted to preserve, the amazing wood, you needed to have a different strategy to if you wanted to preserve the amazing bone. But what's really great about this project, I think, is that we've moved on. The lessons that we've learned from the Starcar project have been used now in Kirsty's NERC Knowledge Exchange Fellowship in conjunction with Historic England, who are the people who have responsibility for looking after heritage sites in the UK, to basically help us understand how we can best safeguard other wetland sites at risk from environmental changes across the globe. So we're really hoping that this work, although it's disastrous for the Starcar site itself, it will actually have a much wider impact in helping us understand and mitigate archaeological loss. So there's been a bit of a whistle-stop tour through all sorts of different types of samples and types of analyses and types of material. I think the challenging matrices that I've been working with is really pertinent to anyone doing analytical science. It's pertinent to forensics, it's pertinent to biologics. It helps us understand what data to trust and what not to. And this kind of multi-analytical complementary approach has been essential to understand, not just the organic parts, but the inorganic parts of the materials that we're looking at. And of course, that brings its challenges of how best to integrate these complex data sets. Understanding degradation and stability, not just on the analytical side, but also on the metabolic side. We've seen some real insights. And I think one of the areas that we're expanding into is that mineral-organic interface, how fascinating it is, and how we can understand how organisms biomineralize far better. And collaboration has been absolutely critical to this. I've worked very closely with lots of different archaeologists, earth scientists, biologists, climate scientists, and it's opened up wonderful new worlds of discovery. So I just want to thank these who are the main contributors to this work, and thank you for your for all the funders who've helped us carry this out, and thank you for your attention.
Thank you, Dr. Penkman, for that informative presentation. We will now start the Q&A portion of the webinar, and we'll address some of the most commonly asked questions by our viewers. If you have any questions you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on the screen, and our speaker will follow up with your questions via email. So let's get started. Our first question is, when you isolate the closed systems of proteins, you said that only time and temperature affect the rates of the protein breakdown. What effect does this have on your dating work?
Yes, so obviously it's a chemical reaction, so it's going to be dictated by time, which is obviously the thing that we're interested in, but also the temperature. So it means that a sample that's sitting in the UK is going to be racemizing at a different rate to a sample that's sitting in equatorial Africa. So obviously we have to take account of that in our dating. And so what we need to do is, when we're building our dating frameworks, we have to build them for a region that has a similar temperature history. Now, these regions are actually pretty large. So for example, from the test that we've been doing, the opercula racemizing in Britain are doing exactly the same, racemizing at the same rates in the middle of Germany. So, you know, it could be a region that is, you know, on the order of, 1,000 kilometers, where we basically build that what's called an amino stratigraphic framework. So you build the dating framework, and then you tie that in to absolute dates using independent geochronology. So yeah, temperature does have an impact, and we can account for that.
Now, are the rates of these reactions the same for different species?
No, so the ordering of the amino acids along the protein chain is obviously very important for the rates of the breakdown, and we were seeing that from the Egg Timer project. And so, because each genus will have different proteins to make their shells or their eggshell or their corals skeleton, then actually they will break down at different rates. One thing we've been doing is kind of tracking how different genera break down, and that's giving us an insight into the processes. But yeah, you wouldn't be able to, for example, compare an eggshell directly with a gastropod shell. You would have to test how they broke down, and you wouldn't be able to compare the data directly across between those. But you can build up dating frameworks using multiple different species.
Now, Dr. Penkman, it looks like we have time for one more question. How can your results help protect sites like Starcar?
So I think one of the things that staggered me the most was how little information we had about the way that a material degrades in those very first few stages, and so the Starcar project has helped us get that data for important materials like bone and wood. Obviously, we're extending that to other types of materials like leather and seeds, but yeah, at least we've got that information for two of the most archaeologically relevant materials. And then through working with our partners, Historic England, and some of the archaeological trusts, by basically trying to put mechanisms in place that enable those changes to be picked up on the short scale, will then mean that we'll be able to identify sites that are at risk. There's a policy, a global policy these days of keeping archaeology in situ. So if an archaeological site is discovered, then the policy is to maybe excavate a very small part of it, but actually to leave most of it unexcavated, because if you do that, then in 50 or 100 years' time, other archaeologists can come with better techniques, with better methods that can then excavate it and therefore recover more information. So it's a very kind of ingrained policy from the last 20 years or so, or what's called in situ preservation, preserving it in the ground where it originally was. Now, that's a great policy, except where it's not safe in situ. And so if, for example, that particular region undergoes through changes in the water table due to environmental change, and that could be, climate driven, it could be driven by human activity in the environment, then suddenly that assumption that the site will be safe forever in the ground is not valid. And so we're working very carefully with these archaeological scientists to try and make sure that we can work out when change is happening, and therefore how valid it is for each individual site to stay preserved in situ, and to be able to put in a plan of action when it's not possible to preserve that site in situ anymore, whether that's recovery or whether that's just giving up on that particular site. So I'm hoping that this data goes in some small way towards better preservation of those types of very important archives of our history.
I would like to once again thank Dr. Penkman for her presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that this webcast will be available for on-demand viewing through January of 2019. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's event. That's all for now. Thank you for joining us, and we hope to see you again soon. Goodbye.